There are two programs I use for image editing. The first one's called Pixelmator. It's essentially Photoshop, but you're allowed to own it instead of renting it by the month. That's the desktop app. That's the one you choose when you want to create something new by hand, when you're still figuring out what the image should be. It's got rich UI, it's fully featured, it's exploratory. You gradually pin down the image you want. The other tool I use is ImageMagick, and that's the command line tool. That's the one you use when you know what you want, but you need to script it up, automate it, scale it out to run over 1 million images. Each of those tools is great at what it does and absolutely terrible at what the other one's good at. And it seems to me that's just an accident of history. There's no fundamental reason why the one-off, user-friendly image editing tool is completely different to the scriptable image editing tool. We could, in theory, have one unified toolset. Well, my guests this week, Keavon and Dennis, would agree with that, but they've taken the idea much further than just a unified toolset. They've designed a language called Graphene, which is all about describing and chaining together image editing operations into a big graph, one that's developer extensible in Rust. And then on top of the language, they've built a user-facing desktop app called Graphite, which looks like Photoshop or Inkscape, but is really just manipulating a tree of graphene primitives, which you can use to make your image, or you could then get your hands back on as a programmer to turn into a script. I'll give you an example. You take a user's image, you send it to your graphic designer, and they design it up and send you back a nicely designed avatar. The file they send you back isn't just one avatar, it's also a program that you could run across all the images for all the users in your system. And the graphic designer never knew they were writing a program. It's a very clever approach to unifying these two needlessly separate worlds through the magic of creating a specialized language and then building tools up upon that language. So I think we should find out how it's all built. I'm your host, Chris Jenkins. This is Developer Voices, and today's voices are Dennis Kobert and Keavon Chambers. I'm joined today by Keavon and Dennis. Gentlemen, how are you?
Hi, I'm doing great.
Yeah, me too.
This is the joy of having two guests at once. There's instantly that race condition on who gets to speak first.
Yeah, and it's more difficult with the latency involved.
Oh, yeah. Well, we'll work around it. I'll try and do some stage management for this conversation, and we'll see how we go. So you two are working on something fun. You're working on an image editor in Rust. And there's a lot we have to get into on that, especially on the technical details, which are juicy. But I guess the first question has to be, and I'll direct this at you, Keavon, why does the world need another image editor?
Yeah, so basically everyone is always asking for one, but it seems that no one has a solution to offer one. So there's definitely an actual community interest amongst many people, both hobbyists and actual professionals, who feel like either their own existing editing software is being abusive to them, or they simply don't have a good free option that exists. If they're using Linux, for example, it's not available. Or if they're using really any operating system, maybe if they're just a kid just learning. That was kind of my background when I was growing up, is having to use like an old purchased copy from an employee discount of Photoshop growing up.
Yeah.
But like I can't get updates to that. So at this point, it's pretty expensive to subscribe. And at the same time, people who are using, for example, GIMP, they're sort of limited by its old interface design approach and a number of limitations that it's able to provide or not able to provide, depending upon your perspective, with the kinds of things that you do with it. So basically, it's really time to inject sort of some fresh ideas into this landscape and really have a nice interface, but also something that's way more flexible by making it also kind of a generative art tool using programmatic concepts from actually borrowed from the 3D industry a lot. There's a lot of node-based generative procedural non-destructive editing approaches, and that is some really, really useful idea, like a useful set of ideas that needs to be brought into this realm of 2D editing.
That is something we've got to get into, because generative has become a loaded term in the past couple of years. Of course,
it's actually developed an entire new term, a new definition with AI, but also generative in the sense that traditional algorithms that can be scripted together to generate content live or based upon dynamic data, or at different resolutions, or being powered by certain data feeds or anything like that. That's all within the realm of what we're ultimately making graphite do.
Okay.
And that's because we have Rust powering everything, and we have our own language built on top of Rust. So that's just a little teaser there, but we'll get into that.
We're going to dive into all of that, but I have to ask you before we go into that. The scope of an image editor, especially you look at something like Photoshop or Word or Excel, and you think, I could do the simple version, but they are now so huge that you don't stand a chance of competing with the full thing, right? Does it not terrify you trying to build an image editor?
It is truly massive in scope. Just unfathomably massive in our roadmap. We have to, actually spell out all the things we know about, and there are so many things we don't know about at the moment that have to be built as well. But all of those that have been built out, that is a decade-long roadmap that we will continue crunching towards as we make progress. But we have been making progress, and it's so far been succeeding. It's still relatively early on, but it's also, it's a useful tool at this point. So. It will take a long time. It's very, very ambitious. I think, Dennis, you can go and give the quote about ambition.
Yeah. So if there's one thing that graphite does not have, it is a lack of ambition.
Yeah, that's basically a quote from me.
Yeah. No, it's a quote from me. It's basically
Oh, no, sorry. Yes, you're right. That's a quote from you.
We end up, we look at something, think, oh, that could fit. That's a good feature. That's useful. We'll just add it to the roadmap. And because this is such a universal approach because graphite has such a universal approach of building an application, just a lot of things fit. And we could extend it to so many realms and do so much useful things. The scope is pretty huge.
For example, someday the same platform that powers the rest of the graphite editor for graphics could also be moved into being like a digital audio workstation, more than a decade down the road. But it is such a generalized approach to making a graphics editor, or to making really any kind of editor, that it's more of a generative scripting tool with a creative editing environment built on top of it, and we can just keep extending that.
You're going to have to take me into that, because I've played with graphite, and it reminded me a bit of Inkscape, that kind of SVG editor thing. There's definitely something deeper going on under the hood, but I didn't immediately see the general editor supreme universe that could be a digital audio workstation one day. So what's your architecture? Give me the high level.
Go ahead, Dennis.
All right. So graphite foremost is an image editor and a vector editor. So one of the principal goals was that we unify both the vector editing and raster editing experience. There shouldn't really be a reason why you need to have two different programs with two different UI concepts for doing images. And this was one of the founding principles. That's what we want to unify. We also don't want to lock the user into, we want the user to be as flexible as possible. And one of the general ideas of graphite is, instead of when the user does something, we record that as the user's intent, but we don't destructively modify something. So we have this idea of both raster, vector, and non-destructivism. Right. The non-destructivism allows us to record whatever a user does, and then non-destructively. I should give an example. So in Photoshop, if you draw something, you have an image. This is developer voices. We have an array of pixels, an array of image types. Then you draw something. The stroke modifies that array of pixels.
Yeah.
And that's done. If the user draws another stroke, you modify the same array again. That's destructive operations. What we do in Graphite is that we record the brushstroke, what the user drew, and then we can apply this at runtime to compute the final texture. So the idea of Graphite is that instead of applying everything the user does, is we record what they do, and we'll get into how we record that. That's the node graph idea. But we record the user intent, and then we can, we can replay that. We can compute what the result would have looked like if we applied the operation directly. We can do that after the fact, and we can modify things.
This is making me think, is that explicitly inspired by what's happening in kind of functional programming and event-driven systems world?
Yes. So
exactly.
Okay.
Exactly. What we do is that, essentially, if we just draw a box in Inkscape, that is, we represent, every operation the user does is reflected in a node graph. The node graph is a visual representation of your document. Within Graphite. So a box would just be a single node that produces a box shape.
Yep.
And we can think of this node as a function. It's a function that doesn't take any input and returns...
Or a width and a height, for example.
Yeah. Yeah, for example. Yeah, it takes width and height as input and returns a box as output. If you then, in the user land, you draw a box. If you then change the color of that same box, instead of making it a node that returns a red box, we instead we modify the node graph to first have a node that creates a box. And the output of this node is then fed into a second node that takes a box as input and returns a red box as output. Like it's a color node. It modifies the data flow.
Oh, yeah. So I've got a function that's from input to redder output. Then presumably I've got nodes like opacity and stroke.
Yeah. Yeah.
This whole library of functions. Right.
And all of this, every node is a function. If you modify something, if you modify the document, we provide tools for you. We provide the same editor experience as you would have in other editors. So for example, if you in Photoshop draw strokes, they would be rasterized as pixels. What we can do instead is that we record the strokes and then have the strokes as input data, feed that through a function which rasterizes them, and we then display the result. What that allows you to do is that you can modify the strokes after the fact. If you didn't like that one squiggle you did, you could modify it, and the rasterized result is updated.
Okay, to what degree can I play around and compose that? If I build up a chain and then I say, actually, I'm going to delete the box at the start of the chain and change it for a function that returns two overlapping circles, do I still get the same pipeline after that?
Yeah, definitely.
Okay, because it really is just a toolkit of functions that transform the image.
Mm-hmm. And our goal really is to make a bunch of useful graphics editing operations, like a big catalog, as many as we possibly can that are useful, so people can really do whatever they want with it and use it as a toolbox.
So if you're making a toolbox, the first question has to be, to what degree is that exposed to the user? I mean, is the user expected to just use these functions or to write them as well?
So we have different levels of abstraction for the different functions, the different nodes, and some of them are intended to be used inside of other nodes. So they're sort of like lower level implementation parts of more abstract nodes, like nodes that do more but have more complexity. So the idea is that they're composed, and we have, just like you have one function in programming, calling other subfunctions, which generally have smaller, more atomic units of complexity and abstraction. Same thing where some of our nodes in our catalog may actually be very technical. They're just we have an unwrap node that actually unwraps an option. But other ones are higher level, for example, like mirroring a shape or doing something else that involves combining shapes together, or involves doing some raster operations that are complex, like dehazing an image. And those may be written purely in Rust, or they may be composed out of subnodes that build up how they're implemented. And the goal is to have lots of different levels of abstraction people can access, but we'll probably categorize them differently. And then additionally, the tooling. So that's like the actual interactive tools that are very similar to Photoshop or Illustrator or Inkscape or GIMP. Those tools, they have a predefined set of nodes that they operate on, and those don't even require working with the node graph, but they provide a completely traditional editing experience that everyone is used to from all those editors. And those operate on the nodes they're used to operating on, but that will be, of course, a subset of all the nodes.
Right. Yeah. I mean, I've played around with this, and you draw a shape and you fill it in, and it feels just like any other image editor, but then there's a button and you can flip over to seeing the node graph, right?
Yeah. So I'd say there are basically like 3 levels of abstractions this user can choose. Like the very basic one is they just use the editor as you would any other editor, and the tools do the modifications in the background. Like we build the document graph for you. You don't have to do anything. You just use the tools. That's like the first level of abstraction. Then you can click on the button to overlay the node graph. Then you can sort of explore what the inner working is, how this all works. That's the second level of abstraction. You can then also start like modifying this, building new nodes, actually work in the editor to modify things. You then can start abstracting the node graph by building your own custom nodes out of existing ones. So for example, if you want to make a clever color reassignment function that reassigns colors based on the rainbow, you could do that and make a node for that. And that is a node built out of other nodes, which can be abstracted and then, shared.
Saved and used in other images.
Yeah, we'll even have a package manager, like an asset store, and it's essentially the equivalent of crates.io or NPM or any other package manager, but it's for
image
our
transformation.
Nodes.
Yeah,
exactly.
And that's sort of the third level of abstraction, and then we have a fourth level of abstraction, which is, it's the lowest one. We literally will allow you to write Rust functions. Currently, that's all defined at compile time, but in the future, we will have support for writing functions at runtime in the editor to modify the code.
Oh, okay. You should speak to the Fireox guy who's doing like live reloading of Rust code.
Which is exactly what we're building towards as well. Yeah, live reloading, cool. Exactly.
Okay, I have to pick up on something you said, this unification of vectors and raster images, because I'm thinking of a node graph. I get this in the image editors I use, that you can turn vectors into rasters, you can turn splines into pixels, but that's usually a one-way operation. You can't turn it back. So that makes me think, how many different kinds of node do you have, and what's the path between them? Because there are some routes you can't transform between.
Yeah, so we sort of have this idea of one-way, things are a one-way street usually. And a large part of the actual node design process is how do we keep things as pure and as useful as possible for as long as possible. So if you're working in vector land before you rasterize, we want to have as much tooling as, we want to build the tools and the nodes to be capable of keeping your data in raster land. But beyond that, there's actually even higher, like additional levels along that spectrum of purity. And for example, a node might start out as a simple vector shape that's described as, let's say text. So text can start out, text is vector based, but also text can represent paragraphs and spacing and different sorts of layout information. So the text data type can become vector, but it actually has a higher level of purity before it becomes just plain old vector paths. And then at some point after that, it then becomes pure old raster. Not pure, opposite of pure, dirty old raster. And then the raster, of course, is the base level because that's what gets sent to your screen. But there's actually even one level of abstraction or purity or whatever we want to call it within the idea of raster, which is that we'll pretty soon move towards talking about what resolution agnostic or adaptive resolution, we sort of have two names for it, refers to. But the general idea is you can zoom in and it will re-render your content at that new resolution, or you export an image at a really high resolution and it will re-render the entire document at that higher resolution. And some raster data is more pure in the sense that it is able to be represented as something that gets re-rendered at the contextual resolution that it's being viewed at, that is being rendered at. Whereas other types of raster data is actually what we call like a bitmap. It's just like it's literally just a width and a height of pixels. It's just a simple image. And in that case, you can't re-render it at different resolutions because it's just a finite amount of actual data. And in fact, it has no position in space even. You'd have to place it into the document and give it positional and transformation information. But otherwise, it just exists as just a piece of data, just an image file.
So are we saying that there's a lot of places on your node graph where it is just a function chain, presumably with caching, which we should talk about, but there must be some operations that say, I'm sorry, that thing you're about to do is going to turn that branch of the tree into a single node and you can't reverse it?
I'm not sure if I understand the question exactly, because the graph is always representing your program.
It's so that there's... it sounds like you're working very hard to ensure that like it's always a function, a chain of functions to a thing. But there are not some operations that say, well, I've got to destructively turn this into a raster. Or if you manage to avoid that throughout.
Yeah.
So
okay.
The way you can get around that, like that is very useful to do. It's basically a cheat code because turning things into raster is very easy. And then you don't worry about anything. The other way of going around it is to pay a hefty performance price and just don't do the rasterization, and we do the rasterization live.
Okay.
So in a sense, what Graphite is very, well, in our architecture is built similar to that of a game engine. We have a game world. Like you think of your document as a scene in the 3D game.
Okay.
And for example, you could, if you build something out of shapes, you can walk up to them and you get a higher resolution render. That's the same. Like if you think about your document as a 3D game world and your camera as like what you're currently looking at, this is what we do in Graphite. We basically re-render the document every frame based on what you're currently looking at. And that is this is what we do with the adaptive resolution system. For example, blurs. You can't, like you usually apply a blur once, and then you can't modify what's beneath it.
Yeah.
So in Photoshop, if you blur something, you can't change what's like the source data. What we can do in Graphite is that if we compute the blur at runtime, we allow you to change the underlying data, and then we have to recompute the blur. So we don't do destructive operations. Instead, we do them at runtime and try our best to provide caching and make that as fast as possible.
Okay. Yeah, I can see that appealing because you always have the thing of like once you've committed to a certain blur level, 2 hours later you can't go back and change the blurred thing. Yes.
Exactly.
Okay, so tell me about caching, because in order to make that performant, you must be making some very difficult decisions about what to cache and what not to.
I will preface this by saying it gets a lot more complicated as a result of the adaptive resolution system. So we'll get into that. But it's actually very different from other traditional node-based editors because we actually have to treat it more like a program, like an actual Rust program, and less like it is simply just flowing one operation into the next operation. So we actually have bi-directional flow of data. So go ahead, Dennis.
Yeah. All right. So basically what we do, well, the concept we're using is also used in programming. It's called memoization, which is used to cache the output of functions. But first, I can explain how our caching model works. Okay. So the way we define a node graph is that every node is a pure function, so to speak, or at least it's idempotent. So given the same inputs, it will always return the same outputs. Okay, that is a very useful property. So we do actually enforce users. Like if users write functions, they have to be idempotent. What that allows us to do is that we can, if we build like a document graph, we can take the leaf nodes and compute the hash of that node. Like all inputs,
yep.
we hashed the inputs, we hashed the node, and now we have a new hash, and this hash is like a function identification. If you are familiar with theoretical computer science, it's sort of the Gödel number. We give each function a number, and this is a unique representation. Given the same inputs, it will always return the same outputs. That's what we do for our entire document. In Graphite, graphs have to be directed and acyclic, so we don't have loops. That makes things a lot easier.
Yeah.
But what this allows us to do is that we do bottom-up, like topological sort, tree traversal, and we then can compute the hashes of every node, given inputs and the node itself. What is the output hash?
This is reminding me of Git.
Yeah, exactly. Same. Yeah, it's a Merkle tree.
More generally, I think it's called a Merkle tree, right?
Yeah.
Yeah.
It's a Merkle tree. So given inputs and thing itself, we compute a hash. And this is what we use for caching, like at least the first layer of caching.
Okay.
So if you have the same input and the same output, if you have the same node, you can assume it will always behave the same. So what we can do is that we just insert cache nodes into our node graph. And the function of a cache node is, if you call it once and the cache is empty, it calls its inputs, computes the result, stores the result in its own struct. And if it's called again, it just returns that result.
So if I have in a simple case, if I have two boxes of the same width and height, you'll only be computing that once, right?
Yes, exactly. Yeah. We automatically deduplicate nodes based on this hash system.
Okay, yep. Do you prune that as you go along? I mean, what do you do about evicting things from the cache? Because that could get huge.
We currently prune if a node has not been used in two subsequent executions of a node graph, then we prune it from the active list, like list of active nodes we keep around.
Okay.
And also, I think at the moment, just because we haven't built something bigger as a system that is a little smarter, but at the moment, I think we also just throw away anything before the last memoized output. Is that correct?
Yes.
Like, so we only store the last evaluation of the.
Yeah. So this was this was easy still if we don't think about any inputs. But like you could argue, if you do the game engine thing and render the same object at a different resolution, the nodes will be the same. The thing is, at that point we have a function. Like again, the entire node, like the entire Graphite document graph is basically a function. It's a function given these viewport parameters, like this zoom level, this viewport translation panning. What's the result pixels that I throw onto the screen?
Right.
And for this function, if you zoom in and out, like the node IDs won't change because nothing in the document graph has changed. But we need to be smart about caching, and we have to take the input arguments into account. And currently, we just recompute it if the input arguments have changed.
So that would be if you change the width or height of the rectangle, for example, then those input arguments change because the hash changes. But if you simply move the camera around, then it does not update that. That's equivalent to generating a game world and then walking around inside of that world. If the character's walking around and the camera's moving, we're not regenerating the world. We don't have to recompile the program that generates the content because we're statically describing a scene that is not changing. But as you walk around, or if you move the camera around, or in this case, move the editor's navigation of the viewport around, that is not changing the scene. The scene is guaranteed to look the same. We just render it at a different resolution, or we render it at a different location, but the scene is static after we have compiled the graph.
That makes sense. Is this why you're saying changing resolution makes things more complicated?
That's why we have to use this Merkle tree approach.
Right. Where the resolution itself is an input to the node graph.
it's a different input. And it does not invalidate the caching. So there's sort of two types of inputs. There's the inputs that pertain to the current way of viewing the static scene, and those do not change the way the caching works. They don't involve the Merkle tree. They don't involve anything like that. But then there is the like if you're actually changing the width of a rectangle or something, you're modifying the scene. So now your actual scene, your actual game world has changed, and in that case, things have to be recomputed. If you blur the rectangle afterwards, you have to go recompute the blur. So in that case, the scene is no longer static; it changed, even if you're viewing it from a different location or you're not viewing it from a different location. So those are the two different types of inputs. One describes the scene; you're actually updating the world, and one of them is just viewing it.
Okay. Yeah, I think I'm with you. So I want to dive into, because there are two parts to this, because beneath all of this, there is a graphics description language of some kind.
Exactly.
That
Yeah,
right?
that is
Graphene.
Yes.
Yeah.
Right. Explain Graphene to me. Why? What does a separate language do? What does it look like?
So Graphene is essentially just a functional programming language, and every node that you draw on the node graph is bijective to a Rust function.
Okay.
Well, at least every atomic node, we do have the concept of allowing you to group nodes together into high-level nodes, like functions. Like you can compose functions and write new functions that contain the different functions. But conceptually, every elemental, like if you double-click into a graphite node, you see the subnetwork, what the node is made of. And for some nodes, you can't go any further because it's just a Rust function.
Right.
And what we do is that we take this description of the user node graph, which is our description. That's the program the user wants to run. And we then compile it and assemble it into at runtime linked Rust functions. So we pass the input, do all our computations. We can also do optimizations if we want. We currently don't have them yet because I want to build a more general tree graph rewriting system first. But we could modify the graph, and then we assemble the output very much like a general like a compiler. And instead of assembling to bytecode, because we're usually first of all, we're mostly targeting WebAssembly right now, like execution in browsers. And what we do instead is that we, at runtime, link Rust functions. We take the compile output, and every atomic node is a Rust function, and we then link them together into one single big function, which we then can call in the runtime. So this is our current execution model.
Okay. Yeah, I can see that. If you think of a picture as being made up of nodes and transformations, it becomes quite a lot like a compiler.
Yeah.
I can definitely see that.
And in that sense, that's the programming language. While Graphite, the editor, that is more like your IDE. And we sort of have a visual IDE instead of a code IDE. And then also we have the node graph, because the node graph is the visual description of your code. That code can be also modified in the editor, but ultimately it is a Graphene program, and Graphene is very much its own language, but it's also kind of a language built out of Rust.
In what sense is it its own language? Because what you've described to me so far sounds like a compiler of Rust functions to a specific target.
Well, it's a compiler of our input graph. It's a graph and not Rust functions yet. The Rust functions, for example, don't have any nesting. In our input compiler, we we do a couple of things. One of the things is that in Rust, you can't have functions with variadic arguments. You have to specify how many arguments a function has. And in Graphite, we want to have nodes that have multiple arguments.
For example, what is the width and the height? So you got to have both descriptions, not just a single description.
Yeah. Okay.
So what we do is we take this high-level user-facing description of what the node graph looks like, and then we can transform that into an actual execution model. Like we do the topological sorting, we flatten the input graph, we resolve inputs, we do type checking. That's another thing. We do type
we've
checking
got to get
in
into
our
that.
compiler.
Okay.
And then we can dynamically link the functions together.
And when you say Graphene is a language, is there like a textual description, or is it entirely constructed in memory by the editor?
Well, it is. We have the .graphite file format.
Okay.
And that
what would I find in one of
.graphite
those?
file format contains a description of the Graphene language, because it's like the embedded document. That's the description.
Is it something I could read, or is it a machine readable description?
It's mostly machine readable. It's a description of. It's a textual description of the visual node graph. So you would usually use the visual node graph.
Okay, that makes sense.
And the use case here, this is something we'll be building soon, is copying like a group of nodes. You can copy them and paste them into Stack Overflow or something, and someone else could copy that text and paste it back into their editor. And that would allow you to give like a group of nodes to somebody else.
Okay.
Yeah, but in the end, that's just a serialization of the visual representation of the format.
Okay. I think we should take one step to the side and just quickly ask why you chose Rust for this particularly. Sounds like maybe a question for you, Dennis.
Well, I didn't make the call. Like I just joined on because the project was written in Rust, or was aiming to be written in Rust. That's why I joined the project. So that's one half of your reason.
Those are some ancillary benefits. We get smart people like Dennis.
Yeah.
But the original rationale was, I think, largely about the tech stack and the ecosystem. We have WGPU, and that is a very, very core part of our goal and meeting our design guidelines. Sorry, our design requirements is having it support both the web and also all the native platforms, and having WGPU as an abstraction layer to be able to take your graphics API calls and put those out if you're on a Mac to Metal, and if you're on Windows to DirectX, and if you're on Android or Linux to or a Chromebook to Vulkan, and if you're on the web, then it will be to the web GPU API that is provided by JavaScript. Although we're still waiting a little bit on all the browsers to actually roll out support for that so we can properly deploy that. We're sort of in this limbo land at the moment with WebGPU not quite being fully deployed, so we're not actually using it by default, and we're using some workarounds until it is, but hopefully within like the next half year, I think it should roll out in all the other browsers. But back to Rust. So WGPU is the crate that provides the implementation of the web GPU API, but for native platforms, and it abstracts over both web GPU for browsers and then also all the other platforms. So that's a huge part of it. The other aspect is that we've always wanted to have a desktop client and a web client, and you can either use C++ with Emscripten, or you can use Rust with WASM bindgen and the WASM backend to provide a WASM binary that can then be loaded into a browser and run by people such as 10 years ago myself, if I was in school, having to not have to download a remote desktop program to remote into my own personal computer at home just to be able to use Blender or Photoshop or whatever professional graphics tools that I could not use on the library computers or the computing lab computers at school. So that has been very much a goal, is having a tool I can use in a browser and also a tool I can use with native performance on desktop. And really there's C++ with Emscripten, or there is Rust. Those are kind of the only tools in town to do heavy duty WebAssembly development.
And I can probably also give you a bit more on why it was actually a good idea. Like that's the initial why we chose it, or why Keavon chose it. Some of the benefits of Rust are, like, first of all, we don't really have to deal with undefined behavior and hunting down memory bugs. That is a huge relief. We did at one point have undefined behavior, and I spent like a week frantically trying to remove every little unsafe, like every last unsafe code in Rust, in Graphite. And it was really annoying and really stressful. And in the end, I found out that like the SIMD implementation in the Chrome browser was just faulty and that just did undefined behavior. It's never the compiler's and never the browser's fault unless it is. And then, well,
yeah, and I believe you can apply to Google for a little medal that says you found a genuine browser bug.
And I had so many Rust compiler issues and like compiler panics. And you've reached a good place when you segfault cause the Rust panic handler to panic. Then you get a double compiler fault. It's fun times.
Yeah.
No, but using Rust is great because it allows you both the fine-grained control, and we do need that because we do need to squeeze out the last little bit of performance and have fine-grained control about what assembly is generated. And it also provides powerful abstractions that allow our application to scale. And that's just a very unique combination. And very fun to work with.
I'm also very much a high-level programmer. I'm normally here coming from like a JavaScript background. I like thinking at the very high level and not thinking about what undefined behavior I just invoked by accident. But Rust actually provides the best of both worlds, and it allows me to be really happy doing high-level programming, but we actually get that C++ level performance and C++ level granularity. It really is just kind of a C++, but with 25 years of hindsight. That is what Rust is.
Okay, yeah, I can totally buy that description of it. It does make me think there are a couple of, if I were naively trying to do this, there were two problems I would instantly expect trying to get a program like this in Rust working on the web. And the first is you said you're dynamically linking Rust functions at runtime. That sounds like that's going to break in a browser.
And well, we don't use the term dynamic linking is a bit overloaded. We're not using dynamic libraries. That's not supported yet at WASM. Okay. We're waiting for that because at that point we can actually generate, we can then at runtime inject new code that has not been compiled into the application. You can
download some blur functions from blur.com.
Yeah. What we do is that we if you think about how the assembly is generated, there's actually an assembly call instruction, which calls a function pointer. You provide it with a function pointer, and it goes to that function and executes that code. What we do is that we essentially exchange that function pointer. It's like if you think about it, and you think like you have a big array of functions, like a global function table. Mm-hmm. And each node knows it's gonna call this function. Okay, but it doesn't know, when we compile the node, it doesn't know which function it's gonna call. And then what we do in the compiler is that we fill in those holes. We say, node red, you call the box function. And then like this, we can chain together the nodes. So the box is colored red.
Yeah. Okay, that makes sense. You got dynamically.
I should also take a moment to explain, because you said the red color calls the box. I don't think we properly explained this so far, but conventional node graphs would take the box, then they'd color it red, then they'd output it. But in our case, because we are starting out from the fully compiled program that's been linked together, we have just a single blob that can be called with an argument, and that argument is going to be the resolution you're viewing it at and the location you're viewing it at. And then that calls, let's say, the red function, the color the box, the color the something red. And you're saying, okay, I need data from this color it red function. And that color it red function says, okay, we need a shape somewhere, but we don't know what the shape is yet. We're going to call the box generator function, and it's going to then take the viewport information as well, the bounds that you're rendering at. And then that box generator function says, oh, you're on screen, or oh, you're off screen. If you're on screen, you produce the coordinates, the actual vector path, give it back to the coloring at red function, and then the coloring red function has the data it needs to color it red, and then return that back. So we're going both directions. We're starting out from the final program output and calling it with the viewport information. And then if something's on screen, we render it. And if something's not on screen, we actually return no data, because that becomes cold. And then it returns no data, and the color red function has nothing to return as well. So it also returns empty data. And the result is you have nothing rendered because there was nothing on screen.
Right. Yeah. This makes me wonder, is it possible, or is there a future where it's possible for me to say, I've designed a graphics pipeline in Graphene, and what's a good example? Where I would like a program that takes a photo, a JPEG I give it at random, and I call it in the command line, and it puts a happy little frame around the edge and makes it grayscale. Could I use that as my graphics processing language rather than just a UI tool?
You hit it on the nail there, and then you could compile it out as a standalone CLI program and invoke it as you would otherwise use like ImageMagick for a similar effect.
Yeah, because I've used ImageMagick for exactly this.
Yeah, you can design it in the editor, a nice WYSIWYG editor. What you see is what you get editor. Do everything you want, expose your inputs, and you could also have text as an input and have like a birthday card generator that takes the name of the person and their age and their photo and their hometown or something, and creates like a nice personalized thing that you can then compile to a standalone program, invoke it as a CLI program, or as something that is like a process that runs as a web server and responds to webhooks or to API requests for like HTTP GET requests. There's a number of ways you could compile this out. This is obviously still the future we're talking about, but that is very, very much exactly what we have planned.
Like what you can, like I did that actually for my bachelor's thesis. I did some like performance optimization with GPU programming. And one of the things I did was write a small like Graphene CLI, which allows you to input a graphite file, so a textual description of the node graph, provide it with input, and it generates the output for you. So we do have like experimental functionality for that implemented, but that is definitely something that you will be able to do, and a use case we want to support.
Yeah.
How far will that go? Because I'm thinking like, I was thinking about the games world and how much of their work is asset pipelines. Could I define a scene that said, okay, if I change my Blender model, please re-render a hero shot for the main character. I'll give you a Blender model. These are the rules to make it look like a pretty thumbnail.
I think that example, not exactly that example, but that was one of the things that inspired the quote with one thing that Graphite does not have is it's a lack of ambition. Because we did think about, if I have a 3D model, couldn't I just plug the 3D model into the node graph and then have a node that renders the 3D model to a picture and then applies some other things to it? And our answer was, we could do that. That's perfectly feasible. You could just use the Blender model as an input to the node graph, and then render, set the camera settings. We would, of course, use a pre-existing renderer. We would need to use something like the Blender renderer and wrap that in Graphite or in Graphene as a node. But you could use that as like a one process, and if you change the 3D model, you could just regenerate the hero shot. Don't need to and apply post-processing, etc.
And you could even do a couple weird things with this. One is you could still use the adaptive resolution system, where as you zoom into your 2D viewport inside of Graphite, inside the editor, that changes the camera render parameters for the 3D scene, and you end up rendering the 3D scene with as much resolution as you need. You never have to pick an arbitrary resolution to render at. You can just keep zooming in, and it'll keep rendering the 3D scene at that viewing resolution. The other weird thing you can do is, because 3D scenes are composed of triangles, you could actually render not to a vector shape, not to raster content, but you could actually render every single triangle as its own vector triangle layer, and then start modifying with your vector effects. You could start modifying the 2D projection of that scene with your vector effects.
Okay, yeah, that would be a horrifyingly large SVG file, but in theory...
Yeah.
But there could be use cases where that's actually useful. Like if you wanted to create, let's say, a torus, and then you want to take that torus and get sort of like a 2.5D effect, but you can then start modifying that torus in vector land. It's perhaps an easier way to render something out of 3D into 2D, but keep it as a vector. Maybe you don't have every single triangle be separate, but you have like the view of all the triangles in the entire model becomes a single vector path, where it's not a bunch of triangles, it's just one single shape composed of all the triangles, but you can still make that into vector land. And that's perhaps a useful way of creating like an outline or a silhouette of something that would be harder to draw by hand. Or you could then rotate it. You could, every frame, because we'll have animation support going with that ambition part, we can have, animation where it will then rotate that object, but keep it going to vector, and then you can do subsequent vector effects.
Yeah. Presumably there is a future where I could handwrite my own Rust functions and say, you know what, I'm going to have my source image data be a REST query or a SQL query.
Mm-hmm. Yeah.
Yeah, okay. This is fun, because I have done stuff like this in shell scripts with ImageMagick, and it's possible, but it's not fun.
Mm-hmm. Yeah. And like one of the unique things about Graphite is that, first of all, one of the main considerations I had for while designing the Graphene language is that I wanted it to be it wanted to give the user as much power as possible. We never want to limit the users in what they can do. So that's also one of the reasons why we don't have a traditional runtime. Usually you would have a runtime, you execute one node, then you manually pass around the data to the second node, and then you run the second node. We don't do that. We don't have a runtime. It's all linked together as a function, and the users could theoretically write their own runtime. They could modify how nodes are executed. And basically, all of the features we've added to Graphene, to our language, have been features that are implemented as nodes. So that's one of the sort of fundamental principles. We want to have a simple language and build the language features out of the language itself. And one of the nice, this paradigm is very powerful. For example, if you want to think about batch processing, in Graphite, we will never have to implement batch processing. Batch processing is basically just, we have a folder of input images. We want to apply this operation to those input images. For example, if you're a photographer and have a speck of dust on your sensor, you would apply the magic eraser tool at this location.
Yeah.
And in Photoshop, you have this batch processing input file. You then apply the operation and get that as an output and save the output. What you could do in Graphite is that you take a sample image, apply the operation, and that's then a program. It's a program from input image to output image with the with the magic eraser.
Yeah.
And what you could then do is you take a step back and think about the entire thing you did, all the editing operations as a program, and then wrap that in a second program, which has a node that reads all the files in a folder, applies your program you did, your image editing, your edits, as a function to those images, and then saves the output again. So something batch processing is just an emergent behavior of our node specification.
Yes, I can start to see now the big ambition here is to make image editing a language first, with all the power that a programming language brings to solving problems.
Exactly.
I like that.
And not just file export. You could also export to a database, because I know you just mentioned SQL queries.
Yeah.
Same for a spreadsheet. Let's say you're designing a trading card game, and you have different images, you have different text for the actual title of the card, you have different stats and abilities, you have different levels, you have flavor text, and all the different information. You could build your entire catalog of cards in a spreadsheet, an Excel spreadsheet or a CSV file, and take that, run it through this batch processor, and output PDF files of every single a card in your entire game, or put them into a grid, put them into like a grid that can be sent to the printer to be printed, one card per page, one card per grid cell within a page, as the specification of the printer requires.
Finally, for next year's RustCon, we have a practical way of making individual Pokemon-style conference passes.
That would also be a really good use case. Yeah.
Okay, so that I'm convinced about the language angle. Let me step back up into the other hard Rust thing that occurred to me that we have to get to complete the picture. Which is, I can see you write this language, you compile it to WASM, all hunky-dory, but then you've got to worry about building a UI on top of this. And that seems like something that isn't fully fleshed out in the Rust world and is taking you into the JavaScript land in WASM world.
That's me!
How have you tackled
I'm
that?
the web developer. I'm also the UI designer, so it's a pretty iterative, it doesn't have to go back and forth between people in different departments, since I'm the one designing the UI and then also implementing it. But it helps that I have a web development background, so I'm.
But is the code base like a mixture of Rust and JavaScript, or is it all Rust?
Yeah. So 90% of the code is Rust, but then that other 10%, that's the web code that I pretty much almost entirely wrote myself. And the way that works is we have some TypeScript, so that of course compiles into JavaScript, and then we have Svelte, and Svelte sort of takes the Rust model of doing as much as possible of the heavy lifting at compile time, wherever possible, do the compile time work instead of runtime work to make it faster ultimately to run on the user's computer. But Svelte transforms a combination of HTML and JavaScript, so you have a single Svelte file that defines a component like a number input or a text field or a slider or a drop-down menu, and I've built like 30 or 40 of these components for all of our different widgets to implement our UI library, like our UI design system for all these different widgets. And each of these are just components. And Svelte's job is to transform the HTML combined with the CSS with some templating built in, so you can actually update different pieces of data live. So the numbers you're seeing in the number input, for example, they change live. But we try and keep this as lightweight and limited as possible. So that way, the actual Svelte files are very small. They account for probably the average size of one of these files might be like 50 lines or something. Some of them are a little bigger. And they take some JavaScript. Sorry, they take a message that's passed from the Rust world and subscribe to. So, for example, we have a layout handler, and a layout handler will take a message received from the Rust world, and it says, create this diff of component changes. So if we have a number input, it will say, okay, replace this number widget with a different number widget that has a different number. And then it displays that. So Svelte then receives the request to change it, and it will go and actually do the update to the web DOM. So the DOM is the tree of elements that are actually HTML code living in your browser and rendered by your browser. So it keeps it pretty lightweight because it's just passing a message saying, replace this widget, and this widget gets replaced. And then the Svelte code has compiled at compile time the exact API calls to swap out the text in that field, for example.
Okay, so it's driven by events from Rustland.
Yeah. And that's actually very useful because we have a well-defined interface for communicating from Rust to JavaScript. And to those familiar with Rust, we actually use nested enums. So we have our front-end messages, and in general, message delivery. That's also an interesting topic, but not quite relevant. So, it's a bit of an aside. But we have a well-defined interface to communicate from Rust to the front end, and we try to keep that as front-end agnostic as possible. So the idea is that in the future, when we have a native backend, we can use the same interface to communicate with the native backend as we do for the current web front-end. No, native front-end, sorry. Yeah, so
native front-end, yeah. Okay.
Same interface for communicating with the native front-end or the web front-end. And that's a nice layer of abstraction into a very clearly defined interface.
Presumably that's two-way as well. You've got a series of messages the front end can send to the to
So
rest.
actually the way that works is when you click on something or you have a keyboard input, so mouse or keyboard inputs, basically, those create events in JavaScript. So the browse, that's just how the web model works in general, is that anything you do with a mouse and keyboard, those produce JavaScript events. And we simply have the components or a global system that forwards all the inputs from the user into the backend. And so if you click on an actual button, the button is going to receive that click, and then it's going to say, oh, I'm supposed to zoom in. It's the zoom button. You click the zoom button, and it immediately, like as soon as it's clicked, its callback, its handler sends a message into the Rust world. And that's how we invoke the Rust side of the architecture, is that call stack begins, like your actual call stack. If you're looking in the debugger, for example, the call stack begins with the click event in JavaScript, and then you run a couple functions, and those functions pretty much immediately call into the Rust world. And then you've got the WebAssembly running. So the web, the actual VM that runs the WebAssembly code does all its stuff, goes and circles around through our messages in the backend, does all the rendering, does any kind of changes that are needed, and then ultimately it produces changes that have to be sent back to update the data in the front end. But again, we keep this very, very lightweight with the front end. So we've seen a number of people who have just tested out Graphite, and they've been commenting on some public forums that we would normally not even be reading because we're not part of that discussion. But I've read people organically in the wild talking about how they feel like this doesn't have the unresponsiveness that a usual web app does because of our careful attention to the architecture to make sure that we have as much responsiveness as possible to feel more like a native app, as people have been describing it, compared to feeling like a web app.
Yeah, but ultimately even though it's all running in the browser, ultimately it's kind of a thin client, thick server architecture.
Exactly.
You're saying.
Yeah, exactly.
Yeah. Okay. Yeah. I can see how that would leave you mostly in Rustland, where you seem to be very happy.
Yep.
So I'm thinking about how getting my hands on this. And my first question with that is actually a more technical one. Is this open source? Can I start hacking around with the code and maybe writing my own functions yet?
Absolutely.
Okay. Tell me about how I would do that.
So I guess I'm the project manager. I can talk about the contribution parts. So it's all open on GitHub. Additionally, our website has a reasonably extensive developer documentation section. If you click on the volunteer button at the top and then go to the development, like the contributor guide, it tells you how to actually install the program and install your development environment. We're using pretty much the common ecosystem thing. So obviously you need to have Rust installed, the Rust compiler and its tool chain that comes with it. There's a couple other programs that are used to kind of combine together the web architecture with the backend architecture. So it's watching for changes with both the Rust code and the JavaScript code. Amazing. And if you change either of them, it will automatically reload the app that you have running in localhost. And you just open it in your browser. And the nice thing is that it's very, very quick to just open in the browser, and it takes half a second or a quarter second or something to open in the browser. So every time you make changes, we still have to wait for the Rust code to compile, which is unfortunate. It takes a little while. I wish that we could find solutions. And if anyone's listening to this and knows good tips and tricks for breaking up the code base into smaller parts that can be compiled independently, that would be very helpful to speed up our development workflow. Anyways, basically we've also got a number of issues that are easily beginner tasks. So people can go and update, either fix bugs or update the functionality for how a tool interacts in a certain situation or a certain edge case, or given certain user input. And then also we've got bigger features, and especially the language parts. That's more Dennis land, and I guess he can talk about that in a second. But all the language parts, so Graphene, and also we didn't touch too much on GPU compilation, but that's also a big part of Graphene, getting more of that graphics programming into the Graphene language. And he talks a little bit earlier about how we try and make nothing be special with the way that the compiler does things, avoiding special case handling for how the compiler works. We want to actually make as much of this built into the language as possible. So actually using the GPU and also compiling your programs into something that the GPU can run as a compute shader, all of that is actually built in the userland side of the Graphene language, rather than being something that is like fundamental to just the runtime, because we have as little of a runtime as possible. So all of that basically is part of Graphene, but it's also the user side of Graphene, the userland side of Graphene, as opposed to the compiler backend. So yeah.
So if someone were a Rust expert and knew the way around shaders, they would be a useful contributor.
They would be amazingly useful, because we've only got Dennis working on Graphene, and that seems to be most commonly the thing that we run into blockages with in terms of our meeting our roadmap goals. Is oftentimes we, like, for example, we want to move on from vector editing to raster editing this year. That is our main goal, is to actually start working on raster editing and become more of a Photoshop or GIMP alternative instead of just being an Inkscape or Illustrator alternative. And that means unblocking the GPU related compilation and rendering. I mean, the GPU related rendering tasks, which is all Graphene land. So Dennis,
and we are also sort of blocked on some ecosystem changes. But that's first of all, you asked if you want to write your own node. That's actually fairly simple. You can last year we redid our entire system, how we define nodes, and now it's basically just you write a function, like you go into a Rust file, write a function, and we then use some special like proc macro magic. It feels like just writing a function, but then magically it's going to appear in the Graphite UI, and we even auto-generate like a settings menu for you, like a properties menu based on the input types your function takes. So that was actually a nice DevX improvement and quality of life improvement that I worked on last year.
Oh, nice.
Yeah, that also makes it easier for like researchers, for example, people with more of a research background in image processing or any other kind of like computational geometry. Actually, there's a number of algorithms. For example, one that we really want to figure out is a convex hull of any shape, so any vector shape. So not just a polyline, but actually a vector shape with Bezier curves, creating a convex hull, which means taking the equivalent of taking that shape and wrapping a rubber band around it, where you level off everything that is concave. That is, I've looked in the literature, and I have not found an algorithm that actually does that on Bezier paths. So that is a great research opportunity amongst many others of a very similar style, where people can actually just write a single function. It doesn't require learning the rest of the code base. Just write a single function, but it implements some kind of image processing algorithm or computational geometry algorithm that does one of the many goals we have for these nodes. So anyone who wants to implement the computational geometry of a convex hull, then it's just a simple function.
I can see that being very appealing to the kinds of people that research those functions and then want to make it look good for and usable for like when they publish. Right? Yeah,
exactly. And it's basically like it's a graphics processing toolbox.
Yeah.
It's a graphics processing toolbox, which means also that like researchers, the research community in general, and academia, they could use it, especially in the future once it's a bit more robust. I think it's probably actually going to be a pretty common choice, where instead of your posting some random code on GitHub as part of their thesis or something, which basically falls into obscurity, it could instead have all the other parts of the ecosystem that would make their lives as researchers easier, and then they can actually publish it onto our future asset store, and then people can actually use it instead of it just sort of falling into obscurity.
Oh yeah, that would be very cool.
And that's also one of the, like, you asked about, well, we talked about how this is all very ambitious, but that's one of the key insights. And one of the advantages of it being open source, if we provide the tools for people to build something, if they use the editor and think, this node would be really great, they could just do that. And that sort of takes the load off our shoulders, and we can, then this all becomes feasible all of a sudden, because building everything ourselves would be just a lot of work, and we're trying to basically build a platform and gain momentum to have volunteers help contribute and build an amazing software together.
Yes, that's the other advantage of turning it into a language. You can then turn features into libraries.
exactly.
That makes a lot of sense. Okay, so final question then. If someone's not feeling quite that ambitious and just wants to use this as an image editor, I'm going to have to ask you to be very honest about this one. Where is it today? Why would I choose it instead of a different image editor today? And where would I not choose it?
Yeah, so 6 months ago, the answer was basically, to be totally honest, it was more of a toy, more of a prototype. It was not something that I would have necessarily recommended people use as part of their ordinary day-to-day workflow, because it just had so many cases where like the type system, you would just keep running into weird edge cases where like two nodes are just not compatible with each other for no particular reason. That was 6 months ago. And additionally, the performance, because Dennis did a huge number of optimizations over the summer. And before then, it was just, you couldn't really do much with it because you'd pretty quickly hit into the performance floor or performance ceiling of what becomes impossible to work with. But 6 months down the road, now that we've had Dennis work on improving all that over the summer, now it's actually reasonably useful if you're looking for a vector editor that doesn't have some like very advanced features. Like there's definitely a number of things that you could do in Inkscape, you could do in Illustrator that we just kind of haven't gotten to. For example, if you draw a shape, any random shape, and you want to round its corners, you'll have to actually go add a node for that as opposed to just using a tool. And that kind of thing might feel a little less intuitive, but it's actually not that hard. You just click on a single button and it adds a node that adds rounded corners. But we have a little bit of limitation as well, where, for example, you can't change how much to round each individual corner. It has to be the same value for all your corners. So it's like little things like that where you might run into a problem, and we haven't supported that yet. But all the general things you need for vector editing, I'd honestly say you're going to have an easier time jumping into it for the first time because the interface is just much more intuitive. You've simply got the tools on the left. You click on the different tools. Those are just the traditional tools that you find in Illustrator. You find in, I guess even Inkscape probably has the same tool library as well. And you have a big canvas in the middle. There's very few buttons to distract you or to make you feel confused or overwhelmed. And you just draw some things. You've got a layer panel. You've got some properties to change the color of something after the fact. It's just a very streamlined, simple editor that I think is pretty useful for anything. If you're doing a laser cutting project or a vinyl cutting project, you could use that for crafting and CNC work. You can also use it for doing graphic design. Pretty much anything that isn't overly advanced. Or if you want to get advanced and start using the node catalog to do things that you actually cannot do in Inkscape or Illustrator or any other vector editing program, you can start doing procedural effects. And for example, what I created was a morphing between different bottles of potions, so different like potion flasks, and it could like morph between like a tall, stout, rectangular one and a very swoopy like bulbous one and a triangular one. And then I could also morph the level of the liquid of the green potion inside of it up and down by just dragging all these sliders around. You can check out I guess the different social media profiles that we've posted that on, and if you want to see that video. But it is something you just could not do in any other vector editor at all.
Nice.
So that's the kind of thing, if you really want to, take more of a programmatic approach, take your developer background and start putting that towards like creative graphics editing. I think the world generally is called like that world of programming to make visual things is called creative coding. That's usually the name, but also generative art. And we would really actually find it very valuable to see people creating those kinds of art, because that helps us figure out what the use cases are. There are so many possibilities that we just never thought of. And if we can just add a few little nodes or a few little settings to make those kinds of things easier, we would, love to see more use cases from people. And that informs the design.
That would actually help me as well, because I make thumbnails every week for YouTube, and I have exactly the same process every time, and I do it from scratch every time.
Yeah.
There's like one caveat, two sort of disclaimers to this. First of all, we don't have a stable document format yet. We are still in flux. We're working on that. We're trying to figure out like the best possible format that doesn't lock us in the future. But currently, we can't guarantee that something you worked on 6 months ago will work in the most current version of Graphite. That is the first thing. The second is that currently the performance for image operations, like we support the image operations, but currently that might be a bit slow.
So that's with pixel-based raster data.
Yeah. So you would need to like test that out to see if that works for you. But those are sort of the two disclaimers I have.
What kind of slow are we talking? Are we talking like the zooming isn't going to be buttery smooth anymore, or is it the user interface is going to chunk?
It depends. It also depends on the resolution of the image you're talking about. Because like with like big 4K images, we also at some point run into memory limits with the browser, because currently WebAssembly only supports up to 4 gigabytes of memory. And if you have if you have like raw images and very big images, that's gonna max out your RAM pretty soon.
Yeah, that makes sense.
So,
and the solution we will have going forward. The solution we have going forward is that two things. One is that we will be loading all of that data onto the GPU, and then it does not have to exist on the CPU, or at least if it does, it can exist in the JavaScript side as opposed to in the WebAssembly memory side. So that will allow us to get over that limitation. But also, I believe they're rolling out support for 64-bit memory addressing in WebAssembly to different browsers over time. I don't know exactly the status on that, but I do know that it is coming down the ecosystem pipeline
proposal.
Okay.
Yeah. So
it sounds like you have a heck of a lot of work ahead of you, but it's all tractable, right? It's all possible.
Yeah.
On which note, I feel like maybe the biggest blocker to your productivity is Dennis, and I should unblock you.
I would say Dennis, his time working on Graphene usually is the biggest blocker for our continued work on the editor.
Okay, excellent. In that case, I will leave you to carry on with it. Dennis and Keavon, thank you very much for taking me through it.
Yeah, thanks a lot. It was a great time. And lots
now
of
can I clone Dennis and get 10 more of him? That would be wonderful. Can we
What's your budget?
Pull him up 10 times on the screen right now as we close this out? He could just talk with a slight delay for each of him. I'm adding extra work for you to edit now.
If you feel like you might be just like Dennis, contact us on this number. Cheers, folks. Thank you, gentlemen. If you want to try Graphite, head to graphite.rs. There's a desktop app, and you can also run it in the browser. Link in the show notes as usual. I have to say, when I first heard about this project, I wasn't expecting something that looked quite as polished as it does. They have done an excellent job, so hat tip to them, and I hope Graphite has a bright future. Give it a try. But before you do, if you've enjoyed this episode, please take a moment to like it, rate it, share it, discuss it over dinner in excruciating detail, even though your partner isn't actually interested in programming. Or is that just me? Either way, we'll be back soon with another episode, so make sure you're subscribed for that. But for now, I've been your host, Chris Jenkins. This has been Developer Voices with Keavon Chambers and Dennis Kobert. Thanks for listening.